Hi. So we're going to talk about fatigue and creep and failure due to these mechanisms today. So first, to define fatigue, fatigue is defined as a form of failure that occurs in structures that are subjected to a dynamic and fluctuating stress. So you might imagine a bridge with cars driving repeatedly over it. So the number of cars on the bridge at any given time might vary. It might be bouncy a little bit if it's a flexible bridge. So you can imagine something like that. The thing about fatigue is that parts can fail even though the maximum stress that the part might be subjected to is much less than the yield stress that you might measure in a tensile testing machine. It's actually responsible for about 90% of life failures, mechanical engineering failures of parts. And the bad part is that it can occur suddenly and without warning, just like a brittle fracture. In fact, the fracture is brittle in nature. If you examine it using fractography, you can see that the surface looks like a brittle fracture surface for part of the surface at least. So here in this picture, there was an interesting failure study done by Sherry Labs. The link is given below if you'd like to read the full study. But the gist of it is these studs or bolts were used to hold on the wheel to a big mining truck. And of course, the wheel just fell straight off one day after the parts had been in service for a long time. And they wanted to know what went on. It turns out that the bolts that they were using were okay for the service that they were being put to, but they were installed incorrectly, and that's why they failed. But they failed after a certain amount of use and just all of a sudden without warning. So they were interested in doing the failure study. You can see here, if you look at the bolts and remember what it looked like when we did those tensile tests, these do look a lot like brittle fracture. So you see these abrupt kind of parts where you have little to no necking, and when we zoom in and look at the parts later, we'll see what the fracture surface actually looks like, but a lot of it will look like a brittle surface. Now, you can simulate fatigue. Of course, if you know that your part is going to be subjected to fatigue, you would like to test the part and see how it's going to perform in service. And so they've designed many machines, fatigue testing apparatuses that can do this for you. So a schematic of it is shown here. Basically, you have something that flexes the part back and forth and rotates the part through so that it gets flexed in multiple directions. And then it can do that for as many cycles as you like. Basically, what they do is they subject it to this sort of beautiful sinusoidal stress. Now, in reality, in service, the stress might not be that beautiful and sinusoidal. It might be much more erratic, but machines do the best they can to simulate that stress. And what they do is they set this stress parameter here. You can change the mean or average stress, and you can change the stress amplitude. You can change the frequency of the oscillations of the stress, and then you just run it to failure. You wait until the part breaks, and you do that for multiple scenarios on the same type of material so that you can get a feel for how that part will perform under a cyclic applied stress. Of course, you want to replicate the actual conditions of service as closely as possible. Here's some images of some testing apparatus that I found online. Basically, the tests will subject a specimen to a stress amplitude that's on the order of 2/3 of the tensile strength, and then what you do is plot the number of cycles to failure versus the stress. So here's a couple images of those plots. So here, what's plotted in this case is the stress amplitude. You could change it to the mean stress. You could plot whatever parameter you're interested in regarding the stress on the y-axis. And then on the x-axis, you plot n, which is the number of cycles to failure. Okay. And so this is a logarithmic plot with cycles to failure here. There's basically two types of fatigue behavior that are seen commonly. One type of fatigue behavior is seen for many different steels. That's the one up here at top with this curve. And then on the bottom curve, you see that for a lot of non-ferrous alloys, and we'll talk about those two scenarios. So for these two different scenarios here, well, for both of them actually, higher stress is actually going to give a lower number of cycles to failure. That's why the curve goes up as it approaches and equals low numbers, okay? It goes up there with your stress amplitude, okay? So the part will fail at a lower number of cycles if you subject it to a higher stress. Not really surprising there. Okay, so next, what you see with some steels, with many steels, is that for these steels, as long as you keep the stress below what's termed a safe level, the part won't fail on you, okay? So you have to keep it at a low stress. And then what you are is you're in this safe region here because the curve will flatten out as it approaches high numbers of cycles. So as long as you keep it below that stress amplitude, then the part will perform well. Okay, that's a steel type behavior. But for some materials, there is no fatigue limit. When you approach that limit, that flattening part of the curve there, that's called the fatigue limit. But for some materials, non-ferrous alloys, there is no fatigue limit. In those cases, they often specify a fatigue strength instead, and the fatigue strength is the stress level for failure at a specified number of cycles. So you say, well, I would like my part to perform for X number of years before I recommend replacement, so what's my fatigue strength at that? And then you design your part so that it will have the specified fatigue strength that you want for the number of cycles to failure that you want. Okay? Okay, now you have to be really careful because those curves that I showed were actually average curves. And statistically, what that means is that half of them are going to fail below that level. If that's your mean curve, then half of them are going to fail below that. A more appropriate treatment might be a series of probability curves. And so if you go on and you become a materials engineer, a materials scientist, I would hope that you would do this sort of thing, okay, and plot a parameter and then stay in the safe limit, even for the low probabilities of failure. Now, another important parameter that sometimes gets cited is the fatigue life. And the fatigue life is the number of cycles to cause failure at a specified stress level. So you specify the stress level, and then you see how long it is until the person has to change that part out, basically. Fatigue, when it starts, it happens in 3 stages. It usually starts off with a crack or a scratch or something like that. So you have a defect in your surface. It could be the threading on your bolt, it could be dent in your surface, a scratch, a rusted spot, whatever. And then at that point, at that defect, a crack will form, okay? And this usually happens at the surface. And then in the second stage, that crack that's formed will advance incrementally with each stress cycle. So every stress cycle, the crack will move a little further, and a little further, and a little further. When it's reached a certain point, some critical size, then the final failure will happen like that. And that's why we say that, you know, fatigue failure happens without warning, because if you don't know the crack is there, all of a sudden the part will just fail one day and you've got yourself what looks like a brittle fracture failure. Now, there's people that do these analyses, like the example that we showed earlier, and then you can look at the fracture surface and see what's going on. There's certain characteristic things that they see in these fatigue parts. So, first of all, this is an image of one of those bolts that failed that we showed on that very first slide. And it's exhibiting something called a beach mark. It's also sometimes called growth rings or clamshells. But anyway, it shows this kind of characteristic layering look, kind of like a tree ring or a growth ring. And what happens there is the crack is advancing, but then, and it's being subjected to stress, but then the part is taken out of service for some time. Maybe everybody goes home for the night, or maybe the part is on a bridge and there's not too many cars on the bridge that late at night, or whatever. Okay, so it's allowed to relax a little bit, and then it's subjected to the stress again, allowed to relax a little bit, subjected, relax, and this forms a very distinct looking pattern that people have learned to recognize as being a sign of fatigue failure. They're bigger, they're visible to the naked eye or with just a simple little handheld lens. Now there's also, if you look at the part under an electron microscope or a high power microscope, you can see what are known as striations inside these beach marks, and the striations are microscopic, and it shows you the advance of the crack front during just one stress cycle and looks like little ripples. All right. Now, down here in the lower right-hand corner is a part from a totally different website that I've cited here. And what that looks like, it'll show you the crack formed, it initiated down here at the bottom, and then you have your kind of beach mark looking pattern down here until the crack advanced far enough, the flaw advanced far enough that boom, you've got your brittle fracture failure, and this is what that surface looks like. Okay? So, so you can figure out a lot from that fractography. Now, since most of these defects, the cracks, start at the surface, anything that you can do to strengthen the surface is a good thing, okay? So you can do what's called shot peening, which introduces defects at the surface, hardening, strain hardening. You can carburize it, you can alloy it, in other words. Alloying will strengthen a part. And you can also remove those stress concentrators. If you have very small radii of curvature, very sharp corners, or anything like that on your part, then your fatigue will want to set in there. So anything that you can do to make the radius of curvature larger would be good. So that's also a good thing to think about. Okay, so that's fatigue and fatigue life. Now let's talk about creep. There's some parts that aren't necessarily subjected to cyclic loads with a stress that varies in time, but there may be a load-bearing type thing. They're supposed to hold a long tensile stress for a long time, and it's not cyclic in nature, just really heavy all the time, for example. Those parts are subjected to creep, okay? Oftentimes these parts, say for example if it's in a jet engine or something like that, this also happens at elevated temperatures. The part gets really hot in service. So if you have kind of a constant load over time at an elevated temperature, your part is subjected to creep. Okay, so there's 3 stages of creep. First of all, when you first place the part in service, the very first day or whatever, first few days, this is called primary creep. And in that, you have, first of all, an instantaneous deformation. The part will deform the instant that you put it in service by some amount. It'll get all stretched out. And then the slope here, this instantaneous deformation, the slope will decrease with time until it reaches the steady state, which is the secondary part. They believe that this decrease in the slope with time of the strain on the part, which is called the creep strain, that decrease in the slope is due to strain hardening. So the part, the metal, is actually getting tougher in service. Then it reaches a plateau where the strain hardening is actually battling with the recovery phase for the part, because remember the part is being subjected to heat. And then you have what looks pretty much like a flat, straight slope there, okay? And then that stage is called secondary creep. The slope of that, here we're plotting creep strain versus time of service, okay? So the slope of this secondary curve is really important because the part spends most of its life in that secondary time frame. It spends most of that time in the secondary stage. The primary stage doesn't take very long, and neither does the tertiary, maybe just a few days for each of them. The secondary strain rate curve can last for years. So that slope right there is very important, and we'll talk more about that. And then finally, it exits the secondary creep and enters the tertiary creep phase, and then the slope actually increases with time until the part finally ruptures. So you want to stay away from that. Creep, as you can imagine, has a temperature dependence. The hotter your part, the more your creep strain rate will be. The faster the creep will occur. For metals, it becomes important mostly at greater than 40% of the melting temperature. Then it really takes off, okay? So that's something to bear in mind. Okay, so let's talk more about that secondary creep regime, okay? Your steady state creep rate is actually constant at a given temperature and stress. You're at that point where the strain hardening is balanced by recovery and you've got that constant looking slope. Okay? So given a temperature, okay, your exponential dependence of your temperature is here, so you have the activation energy for the creep, and as long as that temperature is held constant, this exponential term here is constant. It's e to the minus q over RT, and that's the activation energy for the creep there, that q, and then there's your temperature, okay? Now, your strain rate is the strain, which remember is the change in length over the length. So that's the definition of strain. And a strain rate is how much strain happens per unit time. Okay? So that's your strain rate, epsilon dot. Then you have a material constant in here. Of course, it's going to be a bit different depending on what your material is. And then you have your applied stress times raised to the power of n, your stress exponent. Okay? Now, if you do a log plot of these things, then they look like straight lines. Okay? So your strain rate increases with increasing temperature and increasing stress. Don't worry too much about the units on K. They're really strange, okay? But it's basically just a fit parameter that you would get from the fit for a particular material that you would have. Okay, so let me do an example problem for you so that you can see what some of these creep problems look like. I actually have about 3 examples here to go through. So this is a steel alloy, okay, S590 alloy, and it's 750 millimeters long initially, and it's exposed to a tensile stress of 80 megapascals at 815 degrees Celsius. And so using these plots, what we're going to do is determine the elongation after 5,000 hours, assuming that the instantaneous and primary creep elongation is 1.5 millimeters. So these curves here show the secondary creep behavior, and the instantaneous and primary creep elongation are given to you basically as 1.5 millimeters. So you just need to figure out the secondary part and add it onto the primary. All right, so what we can do is we know that the part was subjected to 80 megapascals at 815 C. So I can look at my plot here and read off for 80 megapascals from the 815 C curve, which is that red curve here, and see what the creep rate is at that value. So reading that off the plot, I get 4 times 10 to the minus 6 inverse hours. Again, the units are a little strange on these things. Just go with it. Okay, so here's my steady state creep rate. That's my epsilon dot. And then what I can do is it asks me for 5,000 hours, so I can multiply my creep rate by my time. So I have 5,000 times 4 times 10 to the minus 6, and I get 0.02, okay? So that's my creep rate. So that'll give me my creep. If I multiply my creep rate by my time, I get my creep. And that's equal to, remember, the strain, which is the change in length over the length, which is the change in length over the initial length of 750 millimeters, okay? So that means I can solve for my elongation, and it's 15 millimeters. And that's for my secondary stage. If I add that to the primary creep, I get 16.5 millimeters of elongation of that part. Hopefully that helps. Okay, here's another question, all right? These are all taken from your book. If the log of the creep rate is plotted versus the log of the stress, as it was previously, a straight line should result with a slope of n, okay? So using the figure, determine n for the S590 alloy at 925 degrees Celsius that's shown here in the orange curve, okay? So we're assuming that the temperature is held constant, so that exponential term e to the minus q over RT, that's a constant value, okay? So for this curve, it's just shown here, and it's some value. And so we're assuming here that epsilon dot is equal to k sigma to the n, okay? So what I'm going to do is I'm just going to choose 2 data points off this line and figure out my slope of that line, and from that I can figure out what my value of n is. So the 2 data points that I chose are the ones that kind of crossed over one of these grid lines, two cross grid lines here. And so the two data points that I chose were 10 to the minus 4 and 60 megapascals. It looked like it intersected there. And 1 inverse hour, or 1 hour, and 200 megapascals. So I chose those two data points. Now, if you look at what the log-log plot would be, if I take the log of both sides of this equation, I get log of my creep rate equals log of k plus n log sigma. And then what's plotted here, though, is the stress on the y-axis, okay? So my slope then would not be n, it would be 1 over n. I rearranged my equation here to show that. So I have 1 over n log of my creep rate equals minus 1 over n log of k. This just becomes my intercept, so it's unimportant to me for my slope calculation. And then that's equal to the log of sigma, okay? So if I want to solve for just my slope, that'll give me my value of 1 over n here. So I plug in for my two data points. My change in my y would be log of 200 minus log of 60. And then the change in the x would be the log of 1 minus the log of 10 to the minus 4. Well, if it's a log base 10, then the log of 1 is just 1, right? And then I have minus 4, okay, because the log of 10 to the minus 4 is minus 4. And then when I do that, I get 0.1046, and that's equal to 1 over n. I solve for n, I get 9.6, so it's basically 10, right? Okay, so here, next question. Estimate the activation energy for creep for the S590 alloy using the stress data at 300 megapascals and temperatures of 650 C and 730 C. Assume N is independent of temperature. Okay? So in my example here, I've got my equation for my creep rate. Epsilon dot is equal to K sigma to the N e to the minus Q over RT. So that's my assumption there. And yet again, what I'm going to do is I'm going to use my two data points. And here, my two data points are for the 300 megapascal data. Okay, so I have two data points, 300 megapascals. And if I look at that, my creep rates for those 300 megapascals, if I look at that intersection of the data, then I get creep rates of 10 to the minus 4 inverse hours and 10 to the minus 2 inverse hours for 650 and 730 C, which were the temperatures cited. Now, K and N are those material constants that don't change because this is for the same material. All these curves are for the same material, the S590 alloy. So those can be assumed to be the same. And sigma is given as 300 megapascals for both. So from this, I've got basically two equations and two unknowns, right? I know my values of my creep rate. I know my values of my temperature. I don't know my K sigma to the N bits, but since I have two equations, I can just subtract those two equations and then that constant drops out. So I end up with the log, a natural log of 10 to the minus 4 minus the natural log of 10 to the minus 2 equals Q over R times 1 over 1003 minus 1 over 923. Okay, and I solve this equation, and I get my Q there, plugging in for the known value of my gas constant, R, 8.314 joules per mole Kelvin. Now, it's really important that you realize that this here, in order to get rid of this exponent, I took a natural log, okay, so that's not a log base 10. So my natural log of 10 to the minus 4 isn't going to give me minus 4 anymore. You have to actually plug it into the calculator, okay? Make sure that you check me out on that. Make sure I did my math right. Okay, now sometimes you want creep data, but it would take a really super long time to obtain because the life of the part, you expect it to be years, for example. But you know that creep happens faster at higher temperatures. So if you want to do a test and you want it to take a reasonable amount of time, maybe you heat the part up to a temperature far above its service temperature, that, you know, far above the temperature you would expect it to have in service, and then you can extrapolate back for the temperatures that it would actually encounter in service and figure it out that way. Okay, so you just do the test at a higher temperature and then figure out what it would happen at a normal temperature. Okay, so we can use what are called Larson-Miller parameters and Larson-Miller plots to figure this out. Now, your Larson-Miller parameter just comes from the same old equation that we've been using. This creep rate is equal to K sigma to the N e to the minus Q over RT, and you just apply a bit of algebra to it. So here's that bit of algebra. If you remember that your creep rate is just your creep strain or strain over a time t, then you can rewrite your equation to look like this, okay? So that your time is equal to your strain over k over sigma to the n times e to the q over rt. So basically I just flipped the equation and multiplied, divided through by my strain. Multiplied through by my strain. Now I'm taking all this stuff out front because I don't really care too much about it. I'm just going to call it a for some constant, right? And then I take the natural log of both sides, and I get log of natural log of t equals natural log of a plus q over rt. Move things over to the other side, subtract it off, multiply through by my temperature, and then I get this relationship. My temperature times the natural log of my time minus the natural log of my constant. Now this is equal to q over r. Okay? Now we can switch this over to a log-based 10 plot so that it more closely matches your book. And all that would do is just introduce a proportionality constant that we don't care too much about anyway, and maybe change what this constant is here inside. Okay? That's all that would do. And then that is our Larson-Miller parameter L. So our Larson-Miller parameter L is the temperature times the log of the time to rupture plus some constant C. And your book says, it tells you that this constant C varies a bit, but it's about 20. I'm sure if you went through and did the math, you could figure out why it's about 20. The rupture lifetime is usually cited in hours, and it varies with the stress. So Larson-Miller plots look like this, okay? Here you have your Larson-Miller parameter times 10 to the 3. So this is 12 times 10 to the 3, 16 times 10 to the 3, so on and so forth, okay? This is yet again for that S590 iron that we've been citing a lot. And then that's plotted versus the stress on the y-axis. So if you're an American materials scientist engineer, you have to get used to English units. This is PSI, okay, not megapascals, but PSI, so there it is on that part of the plot. You can see the SI units in your book if you choose to do so, okay? And so what this does is it shows you the average of a set of curves for these Larson-Miller parameters. What you can do, you can use this to estimate rupture times. So you gather the data at this high temperature yourself, and then you use your Larson-Miller parameter here, which should be equal to a constant, right? That constant Q over R, it should be equal to that constant, and then you can figure out what the value is at the temperature that you're interested in. So for example, here let's estimate the rupture time for a component made of S590 iron at 1073 Kelvin and a stress of 20,000 psi. Okay, so if you go to the stress you're looking at, which is 20,000 psi, and you go over to your curve, then you can read off what your Larson-Miller parameter is there. And it's 24 times 10 to the 3. Okay, so then you plug in 24 times 10 to the 3 for your Larson-Miller parameter. You plug in your temperature there on the left-hand side, and then you solve for that log of the time to rupture. And the time to rupture, once you get rid of that log, is 233 hours. So you can check that out. But that would be how you would maybe extrapolate data when you don't want to run the data at for super long time. You just run it at a higher temperature for a shorter amount of time. Okay, that finishes off what I wanted to say about Chapter 8. In summary, engineering materials are not as strong as predicted by the theory that you might get from a tensile stress. Okay, they can fail at stresses much lower than their yield stress or their tensile stress. And the reason for that is, first of all, because materials are flawed. They have a lot of flaws in them, and those flaws, the scratches, the dings, the dents, or even just voids inside the part that might not be visible to the naked eye, they act as stress concentrators. And those stress concentrators can cause failure at stresses much lower than the theoretical values. If you have a sharp corner in your plot, in your part, you definitely want to get rid of that. You don't want that included in your design because that's a large stress concentration right there that can help out with premature failure, which is totally undesirable. Your failure type is going to depend upon your temperature and your stress, okay? If you have a simple fracture, like it's non-cyclic, your stress is non-cyclic, and your temperatures are relatively low, then your failure stress is going to decrease with increased maximum flaw size, decreased temperature, and increased rate of loading. If you have a fatigue situation with a cyclic stress, then the cycles to fail is going to decrease as your amplitude of stress increases. And the creep, for creep, the time to rupture is going to decrease as your stress or your temperature increases. So that's kind of a summary. All right, see you in class.